Well, hello. Welcome back to IAC 101. This is episode 3, which is going to focus on energy efficiency and industrial cooling systems. Now, normally a third episode in a series like this wouldn't go directly to cooling. There's a lot of other systems that normally get more attention, but we have a big need out there. To be honest, people just don't understand chillers and chiller systems, and that's why we're doing this one next. Okay, so what needs cooling in a factory? Well, both people and processes need cooling. And we tend to cool people with air conditioning, and we're not going to consider that in this episode. We'll consider that as part of a space conditioning episode later on in the series. So we're going to focus at process cooling, and these include a whole variety of needs that you have. Process temperature control, quenching and cooling a mold after you've made something, chemical reactions and processes which often need very precise temperature control, refrigeration, freezing and cold storage. Hey, we make stuff, we got to keep it cool, food product, that kind of stuff. Sometimes we use cooling just to control humidity. And boy, those computers these days generate a huge amount of BTUs that have to be removed from plants. So equipment cooling with an emphasis on data centers is something we would also want to pay a lot of attention. Okay, so let's be very honest about this. The reason we need to pay attention to industrial cooling is that cooling systems are often the least understood, how they work and how they're operating by plants. Uh, Often I have this feeling they believe they're magic machines, very expensive magic machines that make chilled water. Well, let me go one step further. Cooling systems are often the least understood by assessment teams visiting factories who also seem to think that magic machines make chilled water and by some sort of process we don't fully understand. But if we ignore it, we're missing some of the most important opportunities in energy savings. In electricity only plants, sometimes in electricity only plants, we struggle to find big savings. And that's where, again, I would recommend focusing on industrial cooling. Now, in fact, we don't generally cool at the place at the that where we need the cooling. Okay, we will generally find that in most factories that industrial cooling will be indirect, meaning we cool something first, most often a chilled water loop. We'll chill water, and then we'll circulate that water and use heat exchangers to cool whatever processes we need to cool. And so then we have a second system where the cooling is achieved by what we call chillers. They could make cold water. If you need sub-freezing temperatures, you could use ammonia. Very cold temperatures, you could use liquid nitrogen. So we want to look and understand how chillers work. And I apologize if this is going to be boring to some, but I find it almost always worth going through. And if we want to go back 150 years, the question is, how did we cool things? And we cooled them with an ice box. And when I was young, we had an old cottage in the woods, and there was an ice box there. So that's just how old I am. And as you can see from this slide here, that you would harvest ice from the previous winter or from an ice house, and you'd stick it in this one compartment, and then you would hope to keep other things like your milk and your vegetables and your uncooked meats in the other compartments. Well, this didn't work all that great, and sort of by the end of the summer, you guys were out of ice, and what were you going to do? And so we had developed a new device which required us to understand some fundamental physics. And if and these 2 points are key, and so we can't say them enough. The first is when you have a gas and you compress it in a isolated area with insulation around it, its temperature goes up. And so if I raise the temperature of a gas above room temperature, heat will transfer out of that gas. And the second thing is that if I have a liquid that evaporates, okay, it's now gone from a liquid state to a vapor state. And what we find is that that's a much higher energy state for the molecule, so the temperature must drop unless we have energy coming in from somewhere. So evaporating room temperature liquid creates a cold gas, and we generally do this by suddenly dropping the pressure of the liquid. That's it. If we have that physics, we can make all of the chillers that are made today. This is a neat cartoon showing how we use this physics to cool stuff. This is by far the most common way that's used, and it's technically called a vapor compression refrigeration system. Now, and basically, it's a cycle, and we have a refrigerant fluid that we put inside, and it could be one of these freons. There's a lot of different fluids you could put on inside, but the systems are all the same. And so, if we start and we look at this, we'll start with a compressor. So the compressor, because of the physics we talked about, is going to raise the temperature of the refrigerant from wherever it comes in on what looks there as the suction line. It sucks vapor in and puts it out at a much higher temperature, and then it's going to go to the condenser. Now, the condenser is a device which is outdoors, and its job, usually outdoors. Let me not jump to that. Could be outdoors, and it's a heat exchanger whose job is to cool that now hot gas and to cool it down until it changes phase into a liquid. We're going to use gravity, so I'm switching ahead to this particular picture because it's pretty nice. You see that the stuff comes in as a vapor up at the top, and then as it cools and starts changing phase, the liquid will be heavier, and by the bottom, what we're dealing with is entirely liquid, so that we don't need to have any fancy device for separating liquid from gas. We just use our friend gravity. So we had the compressor, which compressed the gas and made it very hot. And then we go into a condenser, which changes that gas back into a liquid. And now we're going to go through what's in this picture, a metering device, which is essentially a valve, which then drops the pressure dramatically. And some of the liquid, some of the liquid will evaporate, greatly reducing the temperature. And we can therefore have a cold material, which we're going to put into our evaporator. And as the evaporator changes all of the liquid to vapor, it will also suck cool in. It will suck energy in from the environment because it's now colder than the environment. Well, we're going to see that we use the gravity again as our friend. If we have some liquid and some vapor together and we want to come out with vapor, well, why don't we come in at the bottom? And as the flow goes through the evaporator to go to the top, letting gravity separate it, and we'll leave the evaporator with 100% vapor, now ready to go back to the compressor. If you really want to look at this cycle in terms of where am I spending money, there is only one place. All these other devices don't have any operational costs. It's just the compressor. And later on, we're going to see when we go to an absorption refrigeration cycle, which you may or may not have heard of, what we do is replace the compressor. But that's for a later slide. So how do we think about efficiency in a compressed air system? Well, to be honest with you, we're not interested in efficiency the way you would look at with a motor system. We're looking at how much heat do you pull out of the refrigerated space over how much does it cost you to drive that compressor. And that comes out to be something that's denoted as the coefficient of performance, the amount of useful cooling divided by the energy usage of the compressor. So what are typical numbers here? And so on this slide, you can see that while it's not easy to measure because you need to have flow rates, there is a wide range of coefficients of performance of chillers in place. In this little chart, you can see that it can get as high as 5, or it can go down to something, in the 2.5, maybe half is good. And this is one of the reasons why we really have to consider upgrading aging chillers. It's a tough sell with industry because these babies are expensive. But if you can show that the efficiency is down to 2.5 and you can double the efficiency, you'll pay off those new chillers very quickly. So let's not forget that the purpose of a chiller is to suck energy from a cooled space, and it comes into our cooler system, and somehow we now need to reject it or dump it back into the atmosphere. Two classic ways to do this. We can do this with essentially a radiator in an air-cooled type of chiller system, or we can use a cooling water loop where we would take water from a cooling tower and bring it through the chiller to take that energy out of there. So the most common is the water cooled chiller systems. And there's a very important reason for this. Not only do we cool with water effectively, but we are able to lower the temperature lower than we would by ambient air by using the physics of evaporative cooling. Now, it's a reasonable question to ask. You say, wow, there is a lot of extra mumbo jumbo to add a cooling tower to a system and another cooling loop and the electricity for the fans of the cooling tower and everything else. And so my standard answer to all this stuff is follow the money. If people are spending money for it, it probably is a good idea. And so that's where this very strange looking slide comes from, because the rest of you probably, if you've watched West Side Story, see it as a romantic retelling of Romeo and Juliet, et cetera, great singing and dancing. Did get Best Picture in 1961, but what I noticed was in the opening credits, before you go down and you look at the gang, that bottom right-hand picture where the gang is getting ready to do a nice dance, you fly in over New York City, and what I'm taken with is even in 1961, most of the tops of the buildings have these telltale fans on cooling towers on the roofs. And so in 1961, it was standard operating procedure. That has not changed until today. Now, if we look at the water-cooled device itself, the chiller, you'll usually notice two very long tubes. These are shell and tube heat exchangers. The lower one will usually be the evaporator. The next one up will be the condenser, and the compressor usually sits on top, so any heat rising from the compressor doesn't go into the evaporator. Now, shell and tube heat exchangers are very good for phase change, and as you know from the previous slides, there are phase changes in both the condenser and the evaporator. Now, either because of space considerations, in many cases, if you put in a retrofit computer system and it needs a chiller to support it, you may not put in a wet cooling tower, but you will just put in a self-contained chiller and air-cooled unit, one shown here in the picture. And if water's expensive, limited, or in reality, yucky. I mean, if you've got a well and the stuff comes out and it's terrible, you may find that using an evaporative cooling tower, the water evaporates, but the junk doesn't. So that can become a very expensive process to deal with. So we see a reasonable number of air-cooled chillers, but and probably more since computer rooms and data centers show up in a lot of places. But there's no question from an efficiency perspective, a water-cooled air chiller is a much better plan. Here's a quick note about the color coding of pipes and the labeling of pipes in these chiller rooms. As I mentioned, these things look like a spaghetti when you get in there. There's pipes going out to the cooling tower and then the chilled water system, and then you have other systems that are usually in your mechanical rooms. So you'd love it if there was an established code which would tell you from the colors whether it was cold or hot at least. And what I'm going to tell you is while there are codes out there, they're not terribly dependable. Usually blue is cool, but in this particular case, the bottom left, now you've got a glycol loop. We talk about chilled water loops, but if the temperature has to go below freezing, you really can't use chilled water, so you'll use glycol, which doesn't freeze, et cetera, et cetera. So the colors will help a little bit, but there are no codes that exist that are of any value to you. So let's move on now. We understand a little bit about how chilled water systems work. So let's talk about some of the low-hanging fruit, the easiest things to do in industrial cooling improvements. And the first is obviously to contain the cold. This is cold water you're passing through your plant, which otherwise is probably making a lot of heat. So you want to separate cool from hot. And it's significant. It's 15% of piping. You'll find in plants it's not 50%, it's 15%. But insulating them is a no-brainer. Problem is not usually the long runs of pipe, but the joints and valves and things that you see, which are often left uninsulated. And this is something that you might pay attention to if you're doing an assessment. So really the big difference between chilled water pipes, cold water pipes, and hot water or hot anything is because being cold, they can condense the air from the room. If the temperature is below the dew point in my room right now is about 58 degrees Fahrenheit, and chilled water is going to be in the 40s. So you would expect there to be condensation if you don't insulate. And a little bit of damage, maintenance failure in your insulation system can mess up the whole thing. Because once you start getting condensation, it makes the insulation wet. And wet insulation is worse than no insulation. If you have wet insulation around a pipe, it actually acts like the pipe is bigger, and you'll lose more energy. Or in the case of chilled water, the water will heat up more because the insulation is wet. You also have the problem of mold that gets formed. And you also have, because these are steel pipes, you're going to have rust. Uh, so one of the things you do on an assessment as you go around is you observe for any kind of leaking, any kind of water. You can actually feel it at the bottom because of gravity of pipes. And so as you walk along, you just put your hand up there and see if there's anything, any water being held by the insulation. Another thing to remember is that the condensation is going to work against vertical piping. So in the picture here on the right, you'll see that in a number of the joints, they do not have them insulated. Well, you say to yourself, well, that's a tiny bit of piping that's not insulated. And yeah, that's great. But the condensation that'll occur there actually will wick down into the insulation and compromise it. So these are easy fixes. I have on the left here a picture of a little Velcro cover. You can install it and remove it. They're very inexpensive, and you can then have a very more competent insulation system. Okay, so after insulation, another common issue is to keep cold pipes or cold spaces away from warmer ones. And this can often be something you would do on the hotter side, insulating hot pipes or putting up barriers to hot areas. So you have to look at that as well. In the next several slides, we're going to demonstrate the need to have multiple chillers operating in order to try and meet load. And so another one of the things to think about is, okay, when you don't have load, are you making sure that the non-operating chillers are isolated from the rest of the system? And the other thing we see out there is sometimes we see cooling done to control humidity or the dew point, and you do much better doing space control, or a spot control, a small space control of humidity, as opposed to cooling a whole space just to get your humidity down. So next, or now, we come to another important idea about chillers, how they're sized and how they operate off load. So let's remember that when you size a chiller, you have to size it for the worst case scenario, the hottest August afternoon. Because if your chillers can't manage it, then you got to shut down. So your chillers are generally oversized for their normal operation. Okay, so here is a diagram below showing the percent of time a single chiller is at a particular load over 6,500 hours of operation. And you can see that it is at 50% load 20% of the time. And then as you start going below 50% of the load, you see that you've got 15, 13, 12, and 11. So you've got about half its operation being operated at 50% load or less. Is this a problem? Well, there you go. Now let's look at the actual performance. This is the kilowatt per ton. So it's sort of inverted from that coefficient of performance, but you want lower here. You want lower kilowatts per ton of cooling. And this is the actual data for a 228-ton chiller. So about 120 tons is about half loaded. And you can see as we go down below half loading, the performance drops dramatically. And so it's a well-known fact that off-loaded chillers, anything loaded 50% or below, is not a good idea. So this sort of offload performance brings up the idea of having multiple chillers and quite honestly having them in different sizes. Okay, I saw one source that said 80% of industrial plants with chillers have more than one chiller. Well, this is the good news. The bad news is if you don't run them correctly, you may not be helping anything. In a case in California, 5% savings in chiller costs was realized when you already had two 200-ton centrifugal chillers, both operating at 45% load. They turned one of them off and ran the other one at 90% load. Okay, saved about $2,800 per year. So we want multiple chillers, but we want those chillers operated intelligently. And those are things that we look at carefully when we do an assessment. So if we're in a plant, it would be really terrific if we could determine the loading of the various chillers and to understand whether they're being operated intelligently or not. And that turns out to be a little tougher than we would hope. A lot of the newer chillers, you can read the load right off of them. They'll have nice displays that you can look at even while they're operating. And you can also hook up a power meter to a data logger, but unfortunately to hook them up, you often have to shut the chiller down, and management may not be too cool to do that. A caution here that coefficient of performance, as opposed to simple load, is more difficult to measure. Energy in, the kW coming, the kilowatt hours going into your chiller, that's easy. You can measure that. But the cooling effect in the chilled water loop or energy rejected in the cooling tower both need temperature differences, that's easy, but they also need flow rates, which are very hard. So normally we end up having to trust chiller documentation to determine the coefficient of performance as a function of load. Now next I want to go into seasonal issues associated with industrial cooling. But we've hit sort of my time mark, so and I got enough to talk about that. We're going to make that into episode 4. So keeping these short so you can now go off and do something useful. This is Mike Muller signing off of episode 3 of IAC 101.